Objectives are discuss the components of an atom, discuss conditions necessary for X-ray production and factors affecting quantity and quality of X-ray photons, discuss the difference between Bremstrom radiation and characteristic radiation, distinguish between particulate and electromagnetic radiation, and identify the properties of X-rays. And I sort of feel like there's other things too that maybe I need to add some objectives to it, but those are some of the main ones. Okay, so the world is made up of matter and energy. Matter is anything that takes up space and has mass. Takes up space, has mass, it's matter. And when matter is altered in some way, when you do something to matter, you make energy. The fundamental unit of matter is called an atom. So an atom consists of the nucleus and its orbiting electrons. They follow these very specific paths called orbits or shells. They're also called shells. The core of the atom or the nucleus is composed of protons and neutrons. And they're inside the nucleus, which is like hardly any space in relation to the atom. Like the atom is like a football field and the nucleus is a football. And then all the electrons are swirling about. So we have the protons, they carry a positive charge, and the neutrons carry no charge. So I kind of think of neutral neutrons. Electrons are tiny negatively charged particles that orbit the nucleus and in those defined pathways. So you see all these here on the, over here, all of these orbiting shells with a corresponding letter. So I think, see, this makes, I want to diverge from my notes, and I'm afraid if I do, I'm going to get off topic. But each one of these carries a different binding energy. So this binding energy term, these are all terms that you probably want to go through your textbook and just write down the vocabulary definition. But each one of these orbiting shells carry a different binding energy, and the closer it is to the nucleus, the stronger the bind. The number of protons in the nucleus equals the number of electrons outside the nucleus, and that determines the atomic number. Binding energy is a force that keeps the electrons in orbit because of the attraction between positive and negative. The binding energy is strong for the electron that's closest. So the K shell, you're going to know, we're going to talk about the K shell in relation to some things having to do with the production of X-ray. So just remember that K shell is closest to the nucleus and it binds the strongest. The binding energy is strong for the electron closer to the nucleus, and it becomes weaker for the outer shell electrons. Ionization is the process or the production of ions due to the ejection of an electron. So when something comes in contact and kicks out an electron, that process is ionization. The atom becomes the positive ion, and the electron that got kicked out is the negative ion. Okay, how are X-rays produced? When high-speed electrons are suddenly decelerated or stopped completely, some of the energy is converted into electromagnetic radiation. So here, think of a car crash. So if a car is hurtling toward a wall and the car is the electron, the minute the car hits the wall and it breaks all apart and pieces go flying, all those pieces that go flying of the car are now X-ray photons. So that's basically what happens in a very condensed nutshell. When electrons get decelerated or they get stopped, things fly off, and what flies off is X-ray photons. So this whole process of the electron decelerating or stopping has happened inside the tube. This happens inside the tube. So we have, you have like the tube and the arm, and then the like the electrical box. Inside that tube head is where this process is taking place. And we will go into that in far more detail as we go along. So conditions necessary for X-ray production: generations of electrons, so you have to have electrons; production of high-speed electrons, so those electrons got to be moving fast; and focusing the electrons, you want to try and get them going in a certain direction to get to a place where they're going to decelerate or break, and then you want them to stop. You want it to have some kind of a mechanism where they stop so they produce the. So generation of electrons. So first we need a source or something to generate lots of electrons, and that we can so we can have our you know, however many we need at our disposal. So we need something that's constantly generating electrons, and that is the job of inside the tube head. There's different parts, and that's the job of the cathode, and part of the cathode is called a tungsten filament. It's a coil of tungsten is a metal. It's a coil of tungsten metal, and it's part of the cathode. When heated up, so when this coil, or that's part of the cathode, when it's heated up, electrons start boiling off of it. So you get a little bit of electricity, little bit of voltage to this cathode and the tungsten coil, and electrons start boiling off of it. They don't go anywhere. They just hover around this coil in what's called the thermionic emissions and an electron cloud. So they're just hovering there at our disposal, ready to be used when we need them. Let's see. The number of available electrons is controlled by the milliamperage. So remember the group that was with me yesterday, one of your little stickies that you had to do for the scavenger hunt said milliamperage. So, and the correct place to put it was on the outside. Well, now I'm giving it away for people who are on Friday, but to put it on the outside where the button is that you actually press, because that's the only place that if you could change milliamperage, which you actually can't change it on our units, but if you could change it, some units allow you to change milliamperage or MA, that's where you would change it. So that's where it says how many MAs for our units. It says 7. So next time you guys go in there, take a peek at it and you'll see it says 65 kVp 7 MA, and that's what ours are stuck at. We can't adjust those. Besides, we can adjust the time. We can adjust the exposure time. So electrical current, it heats the cathode. The cathode consists of the tungsten filament and the focusing cup. We also want to know about the focusing cup. Separation of electrons from the tungsten filament occurs, so they just sort of move away from the actual metal, but they stay close. They boil off in thermionic emission, making an electron cloud. And this is controlled. So how many we have at our disposal is controlled by MA. So that's important for you guys to know that as well. So here's an image of it happening, basically. So this is the tungsten coil, the heated filament, and there's just a cloud of electrons just floating around, bubbling around. So it may be helpful for you to think of the tungsten wire, that tungsten filament, not just as like a solid piece of metal, even though it is, but it might be helpful for you to start thinking about it too in terms of it being made up of tons and billions and billions and billions of tungsten atoms. And those tungsten atoms have electrons orbiting. And so it's those electrons in the tungsten atoms that are what is becoming available to us. So that's why you kind of start like going from like a macro view of what's happening down to like a microscopic view of what's happening. And that's how sometimes that helps. Sometimes it adds confusion. But this is a carbon atom, and the electron rings around it, and then this is showing you the tungsten. Now we're going to look at this again because this is very important when we think about the K shell and the corresponding binding energy. This will come up again. We'll look at this slide again. Okay, so the second thing that must take place is the electrons that are produced must travel at a very high speed. And how does this take place? So how do they get from the coil over to the other side of the little tiny vacuum tube, which is actually very, very tiny? It's actually a very small thing, and we'll look at a picture of it here soon. So how do they go from one side to the other? And this happens because the power source, or the high voltage circuit, or a kV, we call it kVp, kilovoltage. The kVp is a unit of energy, and our X-ray units are all set at 65, by the way. So when that's another thing, just like the MA, we can't adjust that, with one exception, and I'll tell you in a minute. Okay, so when we go to push the button on the outside of the room, when we go to expose the X-ray and actually push the button and it beeps, what has just happened is high voltage energy has been released and has been able to come in and kick off, give enough high voltage to kick off those X-ray, those electrons from the filament that were hovering around in the cloud. Now there's enough of a boost of an energy that they are able to fly over to what we call the anode. So that's on the opposite side, and so they boil off from their cloud, and then when we give them that boost of high voltage from pushing the exposure button on the X-ray, those electrons go from the cathode over to the anode. So the current passes from the cathode, which is negative, to the anode, which is positive. And because opposite charges attract, that's what helps to carry them over. Yeah. Mm-hmm. And I'm going to talk, I don't remember if it's coming up in a slide or if I should, there's a couple things. Oh, no, I will say it here. Okay, so there's a couple, let me get down to that. See, this is what happens when I don't read my notes. Okay, so I'm going to give you a couple tips on how to remember the cathode and the anode and being positive and negative, but just a second here. So, okay, so when you push the button outside of the X-ray room, you hear the beep, and you've just caused a current to pass from the cathode, negative side, with all the electrons, to the anode, which is the positive electrode. So now the anode has a thin plate on it that is also made of tungsten metal. So now on the positive side, there's a very thin plate that's embedded in a copper stem, and that very thin plate is called the tungsten target. So all the electrons that are on this tungsten coil boiling off in the electron cloud, when you push the button and that high voltage comes in, they fly over to the tungsten target. Two tungstens, tungsten filament, tungsten target. And they fly over and they hit that. That's called the tungsten target, and that is embedded in a copper stem. The purpose of the copper stem is to absorb heat. And we'll talk about all of what actually happens and how much heat is produced in just a second. So it's important for you to remember that the cathode is negative and the anode is positive. And if you remember, there's a couple tricks here. So I want to write it here. Does anybody have a piece of scratch paper I could use? Yeah. I don't, if it's good, I hate using good, that looks like good paper. Thank you. Sorry, I should bring in some, but okay. So a couple things for you to remember. Some, what do they call these? Anagrams, or what do you, I can't remember it. So one of them is catnap. So cat for cathode. catnap, cat for cathode, which is negative, A for anode, which is positive. So, yeah.
So you said when we click like on our on-off switch button, and then it moves the electrons by the energy to force the X-rays to go out?
Yes, so when you push the button, you come out of the room and you push the exposure button and you hear that beep. You'll experience it next week if you haven't ever taken X-rays before. You push the exposure button, you hear a beep, and during that beep, the electrons have traveled from out of the electron cloud over to the tungsten target on the anode side. And when they hit the tungsten target on the anode side, that's when they're breaking or decelerating or coming into contact, and what comes off of that are X-ray photons. So it's that going from here to here, having that interaction, and then the X-ray photons come out.
So it goes through the anode first, and then the cathode? They come off of the cathode first. It'll be really helpful in a second when there's a picture too, because I am a visual person. So there will be a picture of this in a second. But first it's the cathode first, which is the negative side, then the anode, which is the positive side. The other way that you can remember this, and could confuse, if this works for you, stick with this, but the other way you could do it is you can write, we say A, B, C, and then we go positive, negative. So then, because that's how we typically say our ABC, we say ABC, and we usually say positive, negative. We don't usually say negative, positive. So the anode is positive, the cathode is negative. So, but that might be confusing because that might make you confused as to what comes first in the machine. So I don't want to confuse you about what comes first in the machine. But if it's on a test and the multiple question just says, is the anode positive or negative, that could help you in that, because that's not asking what comes first. That's just simply saying, is it positive or negative? And so that could help you remember just whether or not. But this is a good way because this doesn't only remind you of if it's positive or negative, but also the order of it. So that can be helpful there. Okay. Stay, pen. All right. So, okay. And then I have a note here about backtracking. Why am I doing that? Also to backtrack slightly, Rx, okay, I already said that. Okay, so I do have a note about the rooms. So and you'll see this when you're in lab, every X-ray room, we have 4, every X-ray room has a set KVP at 65 and a set MA at 7. However, we did get a whole brand new unit in room 264, which is, if it's along this wall here, there's the first 2 here and here. This one, the second one down, is 264, and it has a very, very short PID. It's like super short for the cone. And that room, you can actually adjust the KVP. I don't know that you can adjust the MA, but you can adjust the KVP. But it was easier before when we just told you that all of them were the same. But now we have this new unit where you actually can adjust the KVP from, say, I think you can either do 65 or 70. So you can adjust it in that one room. Okay. So the third thing that's necessary is something that will focus all these jumpy little electrons from shooting off in all different directions. So inside this vacuum tube, you want to try and focus those electrons to get them kind of all moving in the same direction. So that's the job of the focusing cup, and that sort of kind of is like wrapped around the tungsten filament. So that coil of tungsten metal. There's a focusing cup. And that helps them go from the cathode side to the anode side and helps kind of direct them in that general direction.
almost all of the energy that is produced turns to heat. 99% of the energy that is kinetic energy is heat. So that means that 1% of that whole reaction is X-ray photons. So it's not a very efficient system. But it doesn't need to be, because we don't need a lot. So it's actually perfect. But then what happens is this, so when those electrons fly over to the anode and they hit the tungsten target, like I said, it's embedded in a copper stem. It's kind of like just a big chunk of copper. And it absorbs the heat, but then the whole thing, this whole glass vacuum tube where this whole reaction is taking place, is inside of that tube head, but that tube head is filled with oil, all filled with oil. And so it helps to absorb the heat. The copper stem helps to absorb the heat, because most everything that happens in that tube head is heat production. Okay. So here's a picture, a blurry picture. Wish that was a little sharper. I'll have to get maybe a different picture. So here's a picture, and you can see, you can tell, just because you probably likely know what the color of copper. So then it doesn't take a lot to realize that this is the anode side, because this is the copper stem. And you can't really see it, but embedded in the end here would be the tungsten target. And so over here is the cathode side, and you can see it's incredibly short. It's only like separated by like an inch or something. It's a very, very short distance that the electrons go from one side to the other. And this is all lead lined. It's lead lined glass, which means that the X-ray photons cannot get out of this glass tube except for one little tiny window that is unleaded, so that the X-ray photons can come out. So this whole thing is lead lined, except for just a little window. And I don't know where the window is, but somewhere, maybe down here or something. Lined in lead. So the glass is leaded, so that the X-rays just get absorbed in the lead. They can't come out. So they leave one little part of that glass unleaded so that electron or X-rays can come out. Okay, so now these videos are good. This one, I don't know that I'm going to be able to play it. I want to try it, just see if it works. This one is a little bit longer, and I felt like if this is the one I'm thinking of, he kind of was droning on about stuff that wasn't as important. I would encourage you to watch both of them, but this one I think maybe took a little bit longer for the explanation, if I remember correctly. I haven't watched these since last year, so I'm just going to click on this and see if it, oh, it's going to show over here. Hold on, this might not work.
Less astute than the average X-ray student.
I have to get it so that.
Are these different than the ones that you have posted, like the animation films?
Yes, these are different. I think these videos, if I remember correctly, I think these ones just show. Oh, why did it turn dark? I thought it would go to. Hold on. These ones should show just the makeup of the X-ray tube, if I'm remembering correctly. But I want you guys to see it on the screen. How do we do that? Yeah, that's what I. Well, that's strange. a wizard and a unicorn. Okay, let me get. I'm gonna click out of. Okay.
Oh, now it's saying. Now it's going.
Let's
Where do
see.
X-rays come from? Maybe they're created by magical wizards.
Oh.
Maybe they're harvested from unicorns. Maybe X-rays aren't real at all. Obviously, you understand that X-rays are real, and this lesson is about the main principles of X-ray production. X-rays are real, and they have to be created in a very specific way. There's really 3 requirements of X-ray production: a source of electrons, a means of rapidly accelerating or energizing those electrons, and finally a means of rapidly decelerating or de-energizing those electrons. If any of these requirements are missing, X-rays will not be produced. In radiography, all 3 steps of X-ray production take place inside of the X-ray tube. Electrons are produced in the X-ray tube at the cathode filament. The specific process is called thermionic emission, which is the release of electrons, ions, in response to heat. And so it makes sense that it's called thermionic emission. A current running through the filament causes it to become extremely hot. So hot that electrons are actually dissociated from the metal and form an electron cloud around the filament. This is kind of like the filament in an incandescent light bulb. A current running through the light filament creates heat, which creates the light. In an X-ray tube, the filament gets so hot, it actually creates free electrons. A cloud of electrons doesn't do us much good, so what happens next? That's where the unicorns come in. Not really, but the second step of X-ray production is accelerating these electrons, which gives them extremely high kinetic energy. This is accomplished by an electric voltage that we call kilovoltage potential, or better known as kVp. The kVp creates a strong negative charge in the filament that forces the electrons across the X-ray tube. This makes sense, since opposites attract. The electrons are repelled by the negatively charged cathode and attracted to the positively charged anode. The last step in X-ray production is decelerating the electrons. These highly energetic electrons slam into the anode of the X-ray tube, and in the process of decelerating, they actually release their energy as heat and, more importantly, as X-rays. The number of X-rays and the energy of X-rays are actually controlled by you, the technologist, using the MA and the kVp. Increasing the MA, or the tube current, increases the number of electrons produced in the X-ray tube. Increasing the number of electrons increases the number of X-ray photons. And this is the idea of intensity. The effect of kVp is slightly different. Increasing kVp, which is the tube potential, increases the energy of the electrons in the X-ray tube, and increasing the electron energy actually results in increased X-ray energy. So that makes sense. In summary, X-rays are not produced by magic or by unicorns. X-ray production requires 3 basic things: a source of electrons through thermionic emission, a means of accelerating those electrons, that's the kVp, and a means of decelerating the electrons, which is what happens when the electrons slam into the anode. MA is used to control the number of X-rays, and kVp is used to control the energy of those X-rays.
So MA, number of electrons, or and then kVp is energy. And we'll talk with that. Actually, we'll talk more about that in a little bit, because that also does affect the way your image ends up looking, if it's dark or light. So we'll talk about that as well a little bit. I think that's all that we need to know from the video. Okay, let me get out of here and see if I can gracefully get back into where we were. Okay, well, I have to advance way far. Okay, so the other video shows it's more like it's almost like it's a dentist or an instructor or a professor actually holding one and pointing to it. It's like hands-on. He's like looking at it and talking about it, and so you can actually see the pieces of the X-ray tube a little bit better. So click on that one too in the PowerPoint. You'll just have to go in through Moodle, pull up the PowerPoint, and then click on it another time later in this week if you haven't done it already. Okay, so how are you guys feeling so far? Is this good? It takes a minute to like digest it. You know, it'll just, and we'll review it over and over again, and we'll do our activity too. So we want to just kind of tell ourselves the story of how these X-ray photons are created, just kind of make it into like a flowing story from beginning to end, and just knowing all those pieces that are necessary, and then that will help you remember it for the tests, which, by the way, this knowledge will come back again even 2 years later when you're done with everything. These questions they love asking questions about this process on the national board. So you can't forget this. You can forget it for like a minute, and then you gotta remember it again for the national board. Okay, so let's see. So, and we're recording it, so you guys can go back and listen to it, and that will be helpful. I wonder if what screen you're actually seeing is my screen with all my notes, which actually could be very helpful for you. I apologize if that's what it is, because then the PowerPoint's going to be very small. But if you can see, or if, I don't know if this is what's being recorded. So I'm not sure what you're going to be, you'll hear my voice on either one of them. But if you can see my notes, that might be helpful, because then it usually goes into a little more detail. So, but I can't promise you that that's what you'll see. I'm not sure what's being recorded. Okay, so let's see. So next one. So now we're going to talk about the two processes of producing X-rays. Bremstrom is the first process, or that we'll talk about, and then characteristic is the other one. And Bremstrom is the most common process of producing X-rays, and they also call it, I think they call it breaking. So I think it's either they call it breaking or Bremstrom. In all the tests in our assessments for this class, I refer to it as Bremstrom. So it's the most common process, and this is when a bombarding electron, so that's what we call the electron that's flying across to the anode, when a bombarding electron comes hurtling to the tungsten target and gets really close. So now we're going back into atoms again. We're talking about atoms here. This is what's happening in the atoms. The electron gets really close to the nucleus of the tungsten atom, but most of the time it just does a flyby, does a pass by another orbiting electron. So what you can see here is the electron has come flying over from the cathode, and it enters the atom, and it goes by all these electrons, and then but it gets real close to the nucleus, and what happens when it gets to that point but it doesn't hit it is that energy, it like makes it turn, and that whole motion produces energy. That whole reaction of it coming close to the nucleus but not hitting it just produces energy. And that energy is an X-ray photon. So here we have this X-ray photon. Now what does that original, oopsies, go back. Sorry. What does that original bombarding electron do now that it's gone through the atom and changed directions but hasn't actually been used up? So now what happens to it? It goes on and it can do the exact same thing with another and another and another tungsten atom until it's all used up. And so what the main crux of what happens then is that the X-ray photons that are created through Bremstrom radiation end up having various wavelengths, frequencies, energy potentials, because they could come in contact with an outer, weaker electron. They could come in contact with a stronger binding inner orbiting electron, or somewhere in between. So they could have a weak or a stronger X-ray photon penetrating power. Does that make sense? And it can go from one atom to the next to the next. So one bombarding electron can make lots of different wavelengths in different amounts of power, penetrating power, from just one bombarding electron. So it slows down, that electron slows down, changes direction, but doesn't get used up. So the main point to remember with bombarding is that, or with Bremstrom, is that it generally happens below 70 kVp, and it results in many different wavelengths and frequencies, many different, for a X-ray photon, it results in many different wavelengths. So you don't just get one power of X-ray photon, you get some weaker and some stronger. I don't know if I said that super great, but, and we'll talk about wavelengths in a minute here so you can actually visualize wavelengths and frequencies. Okay, so then the next one, any questions there? Yes.
It slows down, it doesn't do what?
It slows down and it like changes directions, but it doesn't actually come in like physical contact. So it still has the potential to come in contact with another atom. So you can see here in the picture, it's the pathway here. It comes in close and then it goes whoop and it turns. And just that motion there has created the X-ray photon. So just the fact that that electron flew in, came close to the nucleus, changed directions, and then went out, created this electron or X-ray photon.
Is that because the nucleus is rotating?
It might be because everything's moving. That's an excellent question, and I don't really know the answer to it. We'll have to get some really sciencey people in here, but that could be because everything's in motion. I really don't know. That's a great question, though. Okay. Characteristics. So we have Bremstrom, characteristic. Characteristic is quite different because the electron, the bombarding electron, that's what we're calling what flew off of the cloud and went over and hit the anode, comes hurtling over from the cathode, hits the tungsten atom on the anode, and knocks out, kicks out, comes in full contact with an electron in the K shell. So a K shell electron gets kicked out. Now the bombarding electron is done. It's totally done. It kicked it out. It's all of its energy. It used it up. The one thing, and that's it. But what happens inside that atom is that it wants to like equalize, or it wants to get back and fill its shells. Remember, they want to like make themselves back to what they were. And so it rearranges, the electrons rearrange, and that rearranging of the electrons is what produces characteristic radiation. So here we see this little red squiggle again, is the X-ray photon that was produced when a bombarding electron comes in, knocks out a K-shell electron, kicks it right out, totally ends the job of the bombarding electron, and then all these other electrons rearrange to fill in the gaps in the other shells that they're trying to fill, and that whole rearranging produces energy, which is an X-ray photon. So this shell jumps into the K, the next one jumps into that, the next one jumps into that, and all that rearranging is what produces the characteristic radiation.
Are those two different ways this one and the previous slide to produce the X-ray photons?
Yeah. So when the electrons are boiled off of the tungsten and they fly over to the anode, and you get that reaction, these are the two different kinds of reaction that could happen. So you could either get this kind of reaction or you could get the Bremstrom reaction. They both end up in X-ray photons. You get X-rays from both reactions, but likely only one is happening or the other. Typically, it's the Bremstrom because a lot of machines, that's just the more common way that an X-ray is produced, is with the Bremstrom. But if a machine is set at 70 or above, it could be the characteristic. But yeah, does that make sense? So they're both producing X-ray photons. They're two different types of X-ray photon production. They just have different parameters for what's creating it. Yeah.
Sorry, I don't know if I fully get it.
Totally okay. It's not, you guys are not being tested on it right this second. We're going to do some more, like talking it through, and then we'll do some, we'll do my little activity. And then, it's a lot to digest. Totally a lot to digest. So I do not expect you guys to walk out of this room and be like, oh, I could take a test and ace it right now, because it's a lot to digest. I would recommend you re-listen to the lecture too after like a day. Let your brain like decompress. Maybe listen to it over the weekend.
So this happens, like either which one, or like each one could happen by, like, okay, so there's the tungsten filament, and it's making electrons, and electrons come shooting out of the cathode to the anode.
Yeah.
Is that happening at the anode, right?
This is happening at the anode.
Okay.
Exactly.
And then the anode is positive?
The anode is positive, yep.
And how is it positive? Like, what makes it positive?
The charge, that's another really good question.
Oh.
Do I know the answer to that? It might be filed away somewhere in my brain. So one side is why are they charged? Is it because of this? It could have something to do, AC/DC, not the band, the like electrical currents.
Yeah.
It possibly could have something to do with that I'm just not bringing forward at the moment. I'm gonna look into that so I can maybe answer that next class. That's a great question.
But it's like positive over here.
Yes.
For some reason. But
Yeah.
it is.
For some
And
reason.
then it just like comes, like the electron shoots over a bunch of them. And then
They go from the negative side to the positive side.
the positive side, and then the positive side is, I forget, it's been a while, but like, are those in the nucleus, the positives, the protons?
Yeah, so protons are positive, electrons are negative, and neutrons are neutral or no charge.
But like the protons and the neutrons are in the nucleus.
Yes,
Okay.
they are in the nucleus.
So then, but like the electrons are trying to go to the nuclei.
Well, they're just kind of heading in that direction. Those free ones that are just flying over there, they're kind of heading toward the atom, and inadvertently they'll go through the orbiting electrons and maybe they'll just pass and never touch the nucleus. So they're not necessarily trying to get to it, because they don't necessarily always do that, but a few of them might. But usually they hit an orbiting electron, or they'll go through and like pass it or get very close to it.
Okay, and that's what produces
Yeah.
X-rays.
Yeah. Okay, so the major difference, I want to make sure, I'm just going to read my notes here. Now the bombarding electron is done. It's used up all of its energy, knocked out the K-shell electron. They rearrange to fill the empty space, and this is what creates the energy. The major difference here are that characteristic radiation is of, good point. So the major difference here is that characteristic radiation is of a consistent energy and wavelength, and only one electron can produce one electron photon. So this is a very big difference between Bremstrom and characteristic. Characteristic, what we're talking about now, one electron, one X-ray photon, consistent energy and wavelength. Bremstrom, one electron can create many different X-ray photons of varying wavelengths and energies. There's that.
Like one electron, many X-rays and wavelengths.
For Bremstrom, one electron can create many X-ray photons with various energies and wavelengths.
Is there a better one? Because I can't remember like which one's the best.
It's not, I don't know. I think it's, like consistently speaking, characteristic, since it's consistent and they're strong, but we don't always need super duper strong ones, because we don't have, like we have soft tissue, they can, but also there's a process to help weed out the really unnecessary radiation that we really don't have any use for, and we don't want it disturbing our biology. And so there's a process. So we'll get to that next, because some of those weaker X-ray photons are just kind of pesky you know, they don't do anything good, and they could potentially cause cellular damage. So we want to weed them out.
Okay.
So in some ways, characteristic maybe sounds more desirable because it's like all, but we don't necessarily need all that much strong, you know, all of that strong X-ray photons to get the job done. So I think they both have their places, but more common is the Bremstrom. The Bremstrom's more common. Okay, so the major difference here, I already said that. Bless you. So this can only happen, so the characteristic X-rays can only be produced if your machine is set at 70 kVp or above, because the binding energy of the electron in the K-shell is 70 keV. And you will see that here. I think it's the next slide. Let me show you here. Yeah. So if you look at this slide, this is the K-shell for the tungsten atom, 69.525 keV, which you can pretty much transverse to the kV, the kilovoltage potential, kVp, is roughly, you can say it's the same thing. This is the binding energy, 69, so that means that your machine has to be set at kVp 70 in order to even produce characteristic. So if our machines in our lab are set at 65, what kind of X-rays are we producing? Bremstrom. So we're producing Bremstrom. Unless you push the button on that one machine and you make it 70, then you'll be doing characteristic. But in general, all of our machines, we produce Bremstrom radiation. Okie dokie. So we have 7 more slides. I'm going to pause this here and let you guys take a 5-minute brain break. So types of radiation. So this is a pretty short explanation. The biggest thing you have to know is that we are focusing on electromagnetic radiation. I'll tell you a few things about particulate radiation, but not a ton. So the main grouping or whatever of what we're talking about is electromagnetic. So we'll focus on electromagnetic radiation because that's what X-rays are. They're electromagnetic radiation. However, the book does mention particulate radiation to give you a kind of a base understanding, and also because this is what cathode rays, which are what Renkin, if you remember on Monday, you guys have seen me a lot this week. So on Monday when we talked about who discovered X-rays, Renkin was working with a cathode ray. That's what he was working with, and that is particulate radiation. All you really need to know about particulate radiation is that it does have mass. It does have mass, and usually it has a charge. So typically we'll say particulate radiation has mass and charge, although I think sometimes it doesn't always have a charge, but it does have mass. And then electromagnetic radiation, what we're dealing with our X-rays, has no mass. So that's a main point, that as far as we need to take our knowledge of this whole rigmarole, we just need to know that particulate radiation does have mass and charge very often, and electromagnetic has no mass. So particulate radiation, just one slide on it. Things like beta particles come from radioactive atoms, and cathode rays are streams of electrons originating in the vacuum, like what Renkin was working on. And we really don't need to know much more than what you see here. So extremely small, they do possess mass, they do contain a charge, alpha particles, things like the electrons, which are the beta particles, cathode rays. So I think there's 1 or 2 questions on the exam about particulate radiation, and I can almost guarantee you it's something about whether or not it has mass or not. I think that I don't even know if there's 2. There might only be 1. So if you need to remember anything, that's pretty much what you need to remember. The different types of electromagnetic radiation are dependent on how they are made and their wavelength. So examples of electromagnetic radiation include radio waves with very long wavelengths, and then gamma rays for things like PET scans that have very high frequency short wavelengths. And we'll look at some visuals of this. So propagation of wavelength energy through space or mass at the speed of light. X-rays produced in the outer electron orbital system. Gamma X-rays emitted from the nucleus of radioactive atoms. So we're not dealing with radioactivity. That's not what we're dealing with. We're dealing with something on a different wavelength than that. So, and it'll be a little bit better when I show you the next slide that shows, or the next one or two slides that show some visuals. So what are some items around your home that are part of electromagnetic spectrum? What can, it says work together, but what can you think of anything in your home that has to do with wavelengths? Microwave. Microwave. Brandon's like, this thing over here. What is it? Yeah, radio, television, a remote control. Yeah, probably. I'm thinking like cell phones, like everything. Aren't we literally swimming in a world of wavelengths? Like I was listening to this talk, and the guy was saying we're swimming in a world of wavelengths, and they're all around us. And if you we're just inundated. And if we could see them, it'd be crazy. But they're doing that, and they're, sending pictures and messages and words and, at the speed of light and stuff like that. And if you tried to explain that to somebody in 32 BC or whatever, it's like a crazy concept, but it is. It's what we're just completely surrounded in. So that's what we're dealing with. Microwaves, all that stuff that we use every day. So the wavelengths, so it's kind of weird because and this again, my knowledge of this caps off pretty quickly. But when you're explaining electromagnetic radiation, it is both a particle and a wave. It's both. It acts like both. And so to understand it, so it moves in a straight line, but it also moves in a wave. So Amy, when she taught this, she had a great way of explaining it like a surfer surfing a wave. The wave is moving, but the surfer is moving in one direction, but the wave, it's riding on a wave, moving around it. So I thought, oh, that kind of helps a little bit. But then this little video here, you can see the same thing. Magnetic field is moving in one way, and the electric field is going in another way, and it's kind of oscillating. So the wavelength is defined as the distance. The actual wavelength is defined as the distance between the crest of one wave and the crest of the next. So a wavelength determines the energy and the penetrating power of the radiation. The shorter the distance, so the more, I'll probably draw some stuff here on this in a second. So the more crests closer together, the stronger the energy. The shorter the wavelength, the higher the energy, and the ability for it to penetrate into matter, so ability for it to go through bone and teeth and cheeks and all that. Frequency refers to the number of wavelengths given in a certain span of time. So if we measure off the wavelengths from here to here, and then we count the crests, that's frequency. So we'll look at that. I'll draw a picture of that here in a second. If you'll notice in this animation, the two fields, the magnetic field and the electric field, are two wave-like fields running perpendicular to each other. However, the radiation or X-rays are always traveling in a straight line. So it's sort of like I said, a surfer who rides a wave. The water moves around them in a wave, but the surfer travels in a straight line. Just one of those trippy, sciencey things that are hard to wrap your mind around. So here you can see from one crest to the other is either a long or short wavelength. And then if we measure the number of crests from a certain specific distance from like here to here, then that's the frequency. How many times do you get that crest in that section of time? That's the frequency. Yeah, let me do this. So wavelength. So you'll have, so if you have my wave's probably going to be horribly uneven. So from the crest of one wave to the crest of the next can either be relatively long or it can be relatively short. So that's the wavelength. So this would be a long one, and this would be a short one, short wavelength. These are weaker. So I think long and lazy, weak wavelengths. These are short and strong. These are going to be more have higher penetrating power. So, and these are what we talk about when we talk about Bremstrom and how those electrons make varying wavelengths and energy potential and various levels of energy for the different X-ray photons. Some come out long and lazy, some come out short and strong. So these are the wavelengths from here to here. And then the frequency would be if we measured here to here and we counted up the crests, that's the frequency. So then if we kept going like this and we counted up here to here, there's way more crests. So this has a higher frequency than this. Because if we measured it in the same distance, you can see there's way more crests in the shorter wavelength. So these are stronger, more penetrating because of their frequency and shorter wavelength. And these are weaker because of their longer wavelengths. So, okay, so this just basically summarizes that. So think short, great penetrating power, high energy, high frequency. They go through stuff. Long, low penetrating, low energy, low frequency, they get absorbed. So they will get absorbed into like the tissue. They'll be, if it gets through let's say it gets all the way through your PID, the X-ray photon gets all the way through the PID, makes it through all of the other little filters that we'll talk about here in a minute, and it gets to your cheek, but it's pretty weak, it might just get absorbed in your cheek before it even gets to the sensor and takes a picture. So we kind of want, ideally, we want the best kind of X-rays to like make it to the end, the finish line, and not just get absorbed in your cheek and cause some cellular damage. So we want the best quality X-ray photons getting to take the picture. Question? No? Okay. So here's just a visual again of those. So we have AM radio, TV, cell phones, radar, remote, TV remote, a light bulb, the sun, X-ray machines. There we are in this. So you can see we'll talk more about non-ionizing and ionizing when we talk about biology, which I think maybe is week 3. So we'll talk a little bit more about that, and then we get to even higher frequencies and things, the radioactive elements and the gamma rays. So this is sort of the spectrum. So these are kind of non-harmful, so, as far as we know, hopefully. And then we have, the midline, and then we go into the ionizing radiation. Okay. So X-rays are measured in nanometers, so they are 1/1000th of an inch. They are very, very tiny. And so you can see here's these wavelengths. This is a bunch of numbers that trust me, you are not going to be tested on any of these numbers. So this is more like interesting informational than something that's going to pop up on a exam. But it just shows the how incredibly tiny they are. So last slide, what do we have here? Okay, so last slide, the characteristics of X-rays. So these are things you have to know. So you might get a question like, all of these are characteristics of X-rays except which of the following. And so, something like that might pop up on an exam. So you want to know that X-rays behave like light. They spread out over a distance and diffuse like light. So you know how when you have a flashlight and it's the beam is strongest at the opening there, and then the light diffuses. X-rays do the same thing. I just realized that I totally just went off in my head, but I realized that my activity has a few elements that was not in this PowerPoint, and I don't understand why I don't have them in the PowerPoint. But I'm gonna incorporate them anyways, and we're just gonna do it, and then you guys it'll be good. Okay. Anyways, so characteristics of X-rays: they behave like a light. They are spread out like the beam of a light. They are invisible. You cannot see X-rays. They do travel in a straight line. So though they diffuse, the ones that as they diffuse, they spread out. So it's not like they change directions, but that's just kind of how they travel. And we'll learn about that in some of the inversion calculations of how that actually works in the weeks to come. They penetrate materials that absorb or reflect visible light. They consist of ionized atoms. And then they produce fluorescence of certain substances. So when Röntgen was working with them, remember something was glowing, he had some screens that were like covered in some kind of a whatever it was, a chemical or something, and it had a certain atomic weight that reacted very specifically with the X-rays, and it made them glow. So that's why he knew it wasn't just the stream of electrons. So they produce fluorescence of certain substances, differentially absorbed in matter. So that means, sometimes they get absorbed in metal, sometimes they make it all the way through like the pulp, and then they end up hitting the sensor. So they're absorbed or penetrate differently, and that's why you get those shades of gray on your sensor. That's why the X-ray looks the way it does, because some are absorbed, some go through. They're just differentially absorbed by matter. And then they do produce a biologic change. So they do, because they're ionizing, they do create a biological change. So that's why we have to know about radiation safety and that sort of thing. So those are all important things to know about the characteristics of X-rays. And that's that. So I'm going to give you guys a minute to finish up your notes, and then I'm going to pass out very randomly. You guys better think this is fun. I've never done this before, so it could be a total disaster. I'm going to stop the recording because that's as much as the lecture.